In this video, we're going to discuss the figure from Schroeder, figure 3.1 at the beginning of chapter 3. And we are also going to discuss the relationship between temperature and energy, where we define 1 divided by the temperature as the derivative, the partial derivative of the entropy with respect to the energy, where we hold N and V constant. Okay, so to think about this, we are going to think about a system where V is always constant, just an Einstein solid. So the Einstein solid essentially has 2 components. It has basically 2 boxes next to one another, box A and box B. And these 2 boxes can trade energy back and forth, but that's it. They can't trade volume, they can't trade particles back and forth. And in this graph, we are plotting the entropy of each of these solids and the total. So this represents the entropy of box A, this represents the entropy of box B, and this represents the total entropy of the combined system, where we know that the total entropy is just the sum of the individual entropies. So if we know entropy A and entropy B, we add them together and we get the total. Okay, what we want to think about now is how does the entropy change as we trade energy back and forth between box A and box B? So we should note here that I am using energy units, whereas our entropy and our temperature are really going to be defined in terms of total energy. So remember that for an Einstein solid, if we have our energy levels, so each of the oscillators within an Einstein solid has discrete energy levels, which are separated by some constant amount of energy. So for example, they could be separated by 0.2 electron volts. So energy level 1 is 0.2 electron volts below energy level 2 is 0.2 electron volts below energy level 3, etc. Our total energy is just equal to the energy per unit multiplied by the number of units. So what we're really going to be interested in is the change in entropy per amount of energy if we want to kind of figure out temperature here. But because our graph is in terms of Q, we'll move back and forth between the 2 ideas where they're just related by a constant. And even when we're looking at the derivative, the slope here of the entropy graph, it's still just related by a constant. So I'll move back and forth between the 2 depending on which I am talking about. And they're really the same idea. It's just units of energy versus actual energy. So now let's look at the change in energy and change in entropy of the system as we trade energy back and forth between box A and box B. And let's see if we can figure out how these slopes are related to temperature. So let's begin here where, let's say QA is 20. All right, so what we're going to do is at 20 units of energy, we're going to trade a little energy from B to A. So we're going to take from B and send energy to A. And what we want to do is we want to see how the total entropy of the system changes. Now, step 1, we can look here and notice that the entropy seems to be increasing at this point as QA increases. So our total entropy, we would think, would increase as we send some energy from B to A, as QA gains energy. And the way that we can think about this is the slope of this line, the ratio of the change in entropy to the change in energy, is a fairly steep slope. That means here we are gaining a lot of entropy per energy, right? So we could write our delta SA, the change in entropy of A, as being the rate of change of our entropy with respect to energy at these constants multiplied by how much energy we gained. This is our rate of change. How fast does entropy increase as energy increases, multiplied by how much energy did we get. We can also do the same thing for entropy B. We can figure out the entropy of B by figuring out the slope of our line. How fast is entropy of B changing? So this is entropy A and this is entropy B. How fast is the slope of the entropy of B changing as it gives entropy to you, or energy, as it gives energy to box A, multiplied by how much energy does it give to box A. But it turns out that the absolute value of the change in the A's entropy is bigger than the absolute value of B's entropy. How do I know that? Well, because this slope is bigger than this slope. That is, the rate of change of A's entropy at this particular energy level to an amount of energy change is bigger than this slope. Now, that means that my total change in entropy should be positive because A is gaining more entropy than B is losing. Note that this slope is negative. B is losing entropy, and it's doing that because it's giving up energy. So as the energy of box A is increasing, the energy of box B is decreasing. So as I move this way on the graph, B is losing energy. As it loses energy, it loses entropy. And therefore, B, this delta SB is going to be a negative value. So we can write our total change in entropy, delta S total, as being the entropy gained by A minus the entropy lost by B, right? And that's going to be my total change in entropy, and this thing is going to be positive. So I am gaining total entropy as I do this. Now, let's see if we can relate this to temperature. Well, step one, A clearly has a lot less energy than B here. And that might make us think that it has a lower temperature, but we need to be a little careful about this argument because we could just have a very small object that's very hot, which would have much less total energy than, say, the Earth, which is much cooler than that object, right? So we have to be careful because the total energy of an object is deeply related to the number of particles that it has. And so hypothetically, we could say, okay, well, if QA, or if box A has many fewer particles than box B, it could be at the same temperature as box B, but have way less energy. So we have to be a little careful about that argument. But what is a good argument is that this slope is steeper, which means that it's going to gain a lot of entropy if it gains energy, and this slope is more shallow, which means it's not going to lose as much entropy when it loses energy. Now let's relate this idea of the slope to the idea of temperature. So if we look here, when the energy in the object is relatively low, the entropy that the object gains for a given amount of energy gain is fairly high. So a little energy gives you a lot of entropy. Whereas when we have a lot of energy in the object, the same energy loss, in this case, as it's giving up energy, leads to a much smaller drop in entropy. The same way of saying this is, you have a lot more microstates, possible states, when you give energy to A and you take energy away from B, when we are here on the graph, when A has small energy and B has large energy. Now, if we think about temperature, if I have two objects that are next to one another, the object that is more warm will tend to give energy to the object that is cooler. And if we couple this with the idea that entropy always tends to increase, total entropy of the universe always tends to increase, then that transfer of heat between the hot object and the cold object must be leading to an increase in total entropy. So what we can say is that within an object with a steep entropy versus energy slope gains energy from an object with a shallow entropy versus energy slope, the total entropy of the system increases. And since we know from the second law of thermodynamics that the total entropy of the universe tends to increase, we can assume that objects with a shallow slope will tend to give energy to objects with a steeper slope. And if we then want to relate that to temperature, we know that hot objects tend to give energy to cold objects. So you would think that if you have a shallow slope, you tend to give energy up. That means you are a hot, high temperature object. If you are a steep slope here, you are a cold, low temperature object that tends to try to get energy, right? And the direction that energy will tend to flow will always depend on the difference between these two slopes. The object with the higher slope of its entropy versus energy graph will tend to gain energy, and the object with the shallower slope will tend to lose energy. If we look at the region here, where the two objects have the same equal and opposite slopes, then the total change in entropy, if I move energy between the two of them, will be zero, right? If I take this relationship, how much entropy did A gain versus how much entropy did B lose when I traded some energy from B to A will be zero here. That means that my entropy is at a maximum and the two objects no longer want to trade energy back and forth. They have reached an equilibrium where it's no longer beneficial in terms of entropy, in terms of number of microstates, for either of the objects to gain any energy. That is what we call equilibrium. Now, we know from experience that if I put two objects together, a hot object and a cold object, energy will pass from the hot object to the cold object until they are the same temperature, which is another hint to us that temperature should be related to this slope. Now, what we would expect is a steep slope to be related to a cold object, because if you have a steep slope, you are interested in gaining energy because you get a lot of entropy when you do that. And we would expect a shallow slope to be a hot object. Okay, well, if I want a steep slope, a high value, to correspond to a low temperature, I can say that 1 over the temperature is my slope. When my slope gets big, my temperature gets small, right? And likewise, when my slope gets small, if I have a shallow slope, then my temperature gets large.